Okay, guys, so the topic for the day is QoS. It's one of the smallest topic that we have uh, for the day, and yeah, it's also the smallest topic of chapter number one. So if you see here under chapter number one, we had multiple topics. So this was the one short topic with which was pending for a long QoS components and QoS policies and the concepts about the QoS. Okay, so what else is pending? And then we are just pending with the SD-WAN and IPv6. Okay, IPv6 of Encore and NRC topic. Let me check the NRC ones. Okay, that was NRC already. Let me check for the Encore portion. Oh, sorry, that was Encore. Let me check for NRC. Okay, so under NRC we have covered MPLS. Yeah, IPv6 is pending and this topic is pending. Yeah, so pretty much done. So under NRC, IPv6 and under Encore, we have this SD-WAN. Okay, so basically the first chapter was all theoretical topic. So as the QS also the topic which we have for the day is once again a theoretical topic. Okay, so let me go ahead. Let me tell you what do we have here. What do you mean by QoS? Quality of service. Okay, I can say this is kind of access list, but special kind of access list. That means they are not about blocking host A to host B or blocking some kind of services. Instead, we are making use of access list to differentiate the traffic. For example, let's say I have host 1 and I got a host 2. Okay, so you know the normal access list. I can place a access list so that I put a restriction from H1, the host 1 reaching H2, right? That's a normal ACL. But in the case of QoS, I'm more interested about to know the data type. For example, is it a telnet data, or is it a SSH data, or is it a voice data, or let's say is it a kind of any other kind of traffic or data type. Okay, might be I can say VoIP, voice over internet. Now what we do is we put this kind of access list to differentiate them. So let's say I put this as uh, traffic 1. Okay, I put this as traffic 2. I can put this as a traffic type 3. Now what is the use by placing them under traffic 1, traffic 2, traffic 3? So basically I can give them some percentage. I can say that if a traffic is coming for telnet, give it 25% of priority out of 100. Okay. Similar way, if I'm receiving a traffic for SSH, give them more priority. Give them 50% of priority. They are very important traffic. Okay. Similar way, if a voice comes, I'm gonna say that give voice the maximum priority, 80% of priority. Okay, now what happens is, let's say if the first packet was for voice, the next packet was for SSH. Might be you have so many traffic going across this wire, right? Basically, what happens if this interface is exhausted, your traffic should drop, right? That is what we have learned so far. If any traffic is received and if the interface is not able to process it, it's going to drop it immediately. Okay, but we don't want that to happen. If my voice traffic is arriving over on this interface, I want 80% of privilege given to voice apart from the other people. Okay, you are good to drop this, you're good to drop this, you're good to queue, put them under queue. But if you get voice or if you get SSH, give the maximum support or treatment so that the packet can be sent across. Okay, so QoS is kind of ACL, but we do much more than the normal behavior of access list. Okay, so we make use of access list to first classify the traffic. In the sense, my ACL is gonna detect whether it's a telnet, SSH, or voice. Okay, and then we will put the QoS service on it, or we will say if it is a traffic 3, give it 80% of bandwidth or privilege. If it is a SSH, give it 50% of privilege. Okay, so collectively ACL QoS, we use the other mechanism in order to tune this QoS. Okay, so let's understand in depth what does this QoS does basically. Okay, so you know that if I have two routers, something like this, if a traffic is coming over here, okay, let's say the host 1 is sending a traffic to host 2. Now the traffic will flow in this direction and reach this direction, right? So what is the work of router? Router will check who is the destination and who is the next or the exit path or the next hop, and then it will forward it, right? Similar thing happen in a kind of switch also. If I have switch and I have host 1 and host 2, now we have the ethernet frame concept. Okay, so what does it happen is when the ethernet frame is arrived here, the switch is gonna do the broadcast or endless broadcast. They will form the MAC address table, and then they will find a way to reach the host 2. Okay, in this case we call it as IP forwarding, and in this case we call it as ethernet broadcast, or I can call it as ARP broadcast. Okay, basically the two things here we see is forwarding or sending to the uplinks, right? But what is the behavior? I mean, if a traffic is arriving here on both the end, what does the router or switch do? It's gonna process it, right? So basically these kind of devices follow two mechanism. Whenever a packet is arrived, it's gonna do two mechanism. One is it's gonna uh, it's gonna see if there is a ACL here or not. If there is no ACL, if this switch ports are not configured with ACL, that means the only work of the router or the switch is to forward it to the upstream, right? And how does it do that? We call the concept of FIFO, that is first in, first out. This is a concept for both router and switch. If some traffic is arriving, it's not gonna see if the traffic is for telnet or voice or SSH, or could be some RDP session, or it could be AAA session. It's gonna treat all the traffic as unique, or not unique, it's common traffic. Okay, That's a general behavior of your router and switch. You send something, it's gonna serve the first come basis traffic. Okay. Now the problem with this kind of scenario is, okay, the voice traffic, okay, they are very sensitive. They're very sensitive. If let's say the voice traffic was getting queued up, there were a lot of packets which were queued up and they are trying to process and send it forward. Now these packet will be getting dropped, and the packet gets dropped. The impact is in real time, because let's say this is a user one who dialed up user two. They are on a call, phone call, and if the packet is getting dropped, so basically you can understand the user from user two point of view, that the voice is getting dropped or lagged, and the other person is not able to understand you, right? So we need to prioritize this kind of traffic. Okay. So how do we prioritize, and what are the factors that impact this traffic quality? Okay. There should be some there should be some factor here, because if I say that if a traffic is sent to this interface, they might put under queuing, they might drop it, they might be free to process every traffic, might be they are choked up. So basically, how is this packet being uh, classified, or I can say how do you make sure that these things should be a good and running fine, so that the packet, that whatever is sent, is smoothly forwarded, right? So there are some concerns here, or I can say the characteristic of network traffic. So the dependency is always on bandwidth. Okay, the bandwidth should be good and up. Okay, there should not be much queue and all those things. Also, it depends on something called as delay, and also it depends on jitters, and also on loss. So these are few characteristic why we need QoS. Okay, so let's check one after one. So let's see what you understand by bandwidth. So let's say if I have two routers, R1 and R2. So if you're sending the traffic, telnet, SSH, voice, VoIP, IPv6 or whatever, okay, you just have one input buffer, okay, or I can say a input queue, and this queue now has to handle all the type of the traffic. Okay, so let's say if one among them is very sensitive, now this voice traffic is also have to follow the queuing, right? It has to follow the queuing. So what gradually happens is there is a chance that this voice traffic gets dropped. Okay, so what we do here is, in or what is suggested is, let's create different queue for different traffic. Okay, so I mean to say, let's create multiple queue here. Say for example, I have a complete different queue for my telnet, I have a different queue for my SSH, I have a queue for voice. Now what happens is, they have certain bandwidth set. I set a bandwidth of 30% to voice, I set a 5% bandwidth to telnet. Now what happens, even if my traffic for voice is less, the bandwidth will be still reserved reserved for voice. Okay, so no matter at any point of time, if the voice comes up, we have a reserved bandwidth, so we call that as bandwidth. Okay, so that's why bandwidth is important, and we set a separate bandwidth for individual traffic qualities or different type of traffics. Okay, delay. Now under delay you have multiple types of delays depending upon where the delay is occurring. So the first one is called as processing delay. All right, the next one we have is queuing delay. We also have serialization delay. Okay, and we have something called as propagation delay. Now first thing, what do you understand by delay? So let's say I sent a traffic, let's say a ping traffic, which took 1 millisecond from A to B. Now that particular ping traffic will also carry a reply back. Okay, so let's say this was a request ping packet and then the reply packet. Now the reply is taking might be 5 millisecond. So what is the total time here? 1 millisecond plus 5 millisecond equals to 6 millisecond. Now this we call it as delay, or we can also call it as round trip time. Okay, a complete 360 degree of the communication, the request and then replied for the same request. Okay, this is called as delay. How much time did it take? So depending upon that delay, the calculation delay, we can have a multiple flavors: processing delay, queuing delay, serialization delay, and propagation delay. So as the name suggests, processing delay is happening due to these tables like MAC address table, could be ARP table, okay, could be the access list. Now what happens is the moment the traffic is being sent to R1, now R1 what it does, it's gonna send it to its routing processor, and then it's gonna check what is the destination for this type of traffic, or if the uh, traffic is meant for access list, it's going to send to the access list table. If it is to the ARP table, it will check. So basically there is processing happening to understand where is the destination connected. Now that is called as processing delay, the processing delay happening within the router or the switch. Now what do you understand by queuing delay? Queuing delay is when the interface is exhausted. Let's say there was some traffic hitting this, okay, and since we are not having QoS configured, so all the traffic are given the equal importance. It could be ping, 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 and in middle of these ping there was a voice traffic, and you're not doing any QoS. So basically what happens is your first in first out is enabled by default, and it's giving privilege to all the traffic. Okay, now that is called as queuing delay. Okay, the delay that is happening due to interface. Okay, interface is not able to process the traffic, so that's a queuing delay. What is serialization delay? Now this delay happens over on the physical interface. Okay, so let's say if these are my two routers and this is my physical connectivity, so this becomes my physical interface and this becomes another physical interface. Now time to send all the bits. Okay, so whatever was sent on this interface, now what is the delay or what is the time that's required to send all the traffic over on the physical interface? So far it was in incoming traffic, once again on the interface. Now it's about outgoing interface. How much time does it take for your outgoing interface to send the traffic? Okay, What is propagation delay? Now let's say if I have host 1 who is in New York and I have host 2 who is in, uh, just name some other city of might be a different country, or let's say Egypt. Okay. Now propagation delay is something where the packets took lot of time to propagate. Okay. So let's say if this was like 100 or 1000 feet of fiber optics. Okay. So what is the propagation delay for the packet over here? So that is labeled as propagation delay, the time taken for your data to cross the physical medium. Okay. So this is under delay. Okay. Once again, we are now going through the characteristic of network traffic. So we have bandwidth, we have delay, and now let's check the third one, which is called as jitter. And also we have something called as loss. Okay. Now what is jitter? Jitter is one way delay in the string. Okay. In the sense, let's say if a phone, IP phone, was sending some kind of traffic, a bulky traffic. Okay. It was sending a bulky traffic from A to B. Now let's assume this whole data was too big enough to send at one particular shot. That means I have to fragment the whole bulky packet into multiple packets. So let's say I fragment into first packet, second packet, third packet, and fourth packet. And every time I'm sending my packet one after one. So let's say I sent one, I'm sending packet two, I'm sending packet 3 and 4. Okay. Now jitter is the time taken for this packet in one way direction for each packet. Okay. So let's say for first packet, it took 10 millisecond, but the second packet took 20 millisecond. Third packet is taking might be 35 millisecond. Fourth packet is taking 5 millisecond. So you never know which path might be. There are multiple paths. One path was choked up. That's why it took a lot of time. Whereas the other path were all good, so uh, they reached the destination sooner enough. Okay. So jitter is one way delay. So we are talking about one way delay, and that is happening when, let's say that we are sending a voice traffic. We had to fragment the traffic into 10 smaller packet, and each packet takes its own time to send from host 1 to host B. So there will be a different time for now, for there will be a propagation time for that, and all this 10 packet will not be sent like in 1 millisecond. Okay. Might be the first one will take 1 millisecond, the second one takes 5 millisecond. It's about the path which the traffic is propagating. Okay. So there could be multiple path for to reach the destination, right? So it's always happening parallelly. If the packet one went on one route, the second packet might take the third route or fourth route, whichever is free. Okay. Whichever is free to propagate it. Now we never know that that particular third path might be choked up in between, or there could be some congestion or something. Okay. So we call this kind of characteristic as jitter. And finally we have loss, which is quite a simple. If I'm sending 100 packet from host A to B, but I only receive 5 packets. Now I can say that 95% of packet just dropped. right? So this is loss. Okay, 95% got dropped, which is a loss for me. So this is a characteristic of network traffic: bandwidth, delay, jitter, and loss. Now let's see the different traffic type. Okay, because if we know what are the different traffic type, might be then we can classify, we can do the QoS shaping, or might be we can look into it, right? So we need to understand what are the different traffic type in the enterprise, which can be classified as QoS, or we can put some rules and regulation, right? So the first traffic type is batch application. The second traffic type is interactive interactive application, and the third traffic here is called as voice and video application. So pretty much it's very simple to even guess what am I gonna talk about. So basically this is how you generate the traffic. So normally how do we generate the traffic? Let's say if I go to my WhatsApp GUI, if I write a text message to someone, so basically I'm making use of that application to generate the traffic, and rest is all we know as a network engineer what happens in the OSI layer, right? So basically it is we guys who use this kind of application. We do something and the traffic get generated. A simple example could be if you're downloading some MP3 song. So basically we go to the website, we click on download, and the data is traveling from from that particular server to our computer, right? Or if I'm initiating a video conference call, so basically it's an application which we use in the batch application. It could be MP3 website. It could be a simple Cisco download website where we download those iOS bin file, right? We click on download, and the data start flowing, right? So these are all considered as batch application. Okay, and the data will get fragmented because it's not possible that I download a 1 GB of file in single shot. Okay, so basically my data, which is 1 GB, okay, it doesn't mean that the internet is going to carry the whole 1 GB of data in one single shot. Okay, so this 1 GB will be divided into multiple smaller fragments. Okay, might be 5 thousands of fragments, and each small fragment gets added up with the L2 header, L3 header, L4 header, and then it will be passed on to the next person, or I can say the receiver. Okay, and luckily what happens, these fragmentation carry something called a sequence. If it is a first bit, we have sequence 0. Let's say if the second sequence is traveling, we set the sequence of 1. If I have sequence 3, I set it as sequence 3, and finally I set the last sequence number, and I tell that this is the end of this packet. Now on the receiving side, they check the sequence number and then they start placing them one after one. Now what happens once they receive all the 5,000 smaller fragmented packet? They are now the whole single data. Say for example your image. If you go to Google, if you download any image, right, the whole image don't get downloaded at one single shot. Those images has to be cut into multiple small fragment. Each fragment will be placed, or will be added up with those header L2, L3, and then it will be sent over on the wire connection or the wired connection. And on the receiving side, this small fragmented data gets reassembled. And how does my computer know that this is the first piece of it, this is going to be second, third? That's because of the sequence number. Okay, so basically we need this application, we need this this kind of application who will initiate the traffic. In the end, in the back end, the the data gets fragmented, and then it will be sent. Okay. So let's go to the next one. Now, what is interactive application? Interactive application is something where the application is gonna prompt us for yes or no sorts of data propagation. Say for example, when I have a H1 to H2 connection, let's say I took a telnet prompt. Okay. So when I take a telnet prompt on my console, when those public crypto certificates, or those certificates are being loaded up, when I do a telnet from H1 to H2, I get the certificates offered, and then I also get something called as, do you wanna continue, yes or no, right? So when we type yes, we get into the next step. So basically these are all interactive application where I say yes or no, and then the traffic gets initiated or corresponded. Otherwise it will just shut down its window. Okay. First one is batch application, all your application, all your tools, or all your messengers. Then we have interactive application like your putty session, RDP session, consoles, where it is going to ask you. Okay. And then we also have something called as voice and video application. Now the most sensitive traffic we see is in the case of voice and video, because these are something which we don't have to be bothered about, but voice is very sensitive. Okay. Because that happens in real time, and these traffic have something called as Kodak. Okay. So this is a feature which gets added up to the uh, data. Like for example, in the case of your normal packet, we saw L2 header, L3 header, L4 header. Similar way, in the case of voice and video, okay, if this is my data, we see the Kodak getting added up as a header. Okay. So why this happens is, these analog signals gets converted to digital signals, and then we send it across on the wired connection. So there is uh, there's a need where we define the header, saying that this is a so and so sorts of the traffic. Otherwise the receiver will not know what kind of traffic it is, and might be the chances are that it drop it. Okay. So basically, even in our normal data traffic, the same thing happens. We encapsulate something, and on the other side we just decapsulate the same traffic, right? If I'm sending simple SSH traffic, it's which is encapsulated, and on the other side the same traffic will be decrypted or decapsulated. Okay. All right. So these are some sorts of traffic. Okay. Now let's talk that important topic, or the important topic of the QoS, which is called as QoS tool. Now here you gonna see what are the different tools that we use for classification of the traffic, marking the bandwidth, settings the delay for the non-required traffic, right? So there are some tools that we use. So let's say the first tool is classification and marking. Okay. The second tool is queuing. We also call it as congestion management. What else do we have? We have the most important feature called as shaping and policing. This is very important topic from cert, from interview. And finally we also have something called as congestion avoidance. Okay, so these are the four QoS tool that we are gonna see them, and we're gonna understand them. How is QoS implemented on an real devices? Okay, so let's say I had router 1 and I had router 2. I straight away take a telnet. Okay, if I take a telnet and if I do a quick Wireshark analysis, what do I understand from that Wireshark? I understand who is the source, who is the destination, right? Who is the source port, and who is the destination port, or what is the destination port. Now this is most important thing. Destination port. The destination port is gonna reveal me if it is a TCP, if it is a UDP, if I say it's a port number 80. So basically it's gonna be a STTP, right? If it is a 23, I'm gonna say that it's a telnet traffic. If the port number says it's 22, I'm gonna say SSH, right? So this is very important for me to understand what kind of traffic was being sent from R1 to R2. Okay, now what I do is I put some access list. Where should I put the access list? I can put the access list straight away here. I put a access list, and I set the traffic match. I'm gonna say that access list telnet. Okay, and this access list I'm gonna say permit, let's say 1.1.1.1 traffic, 1.1.1.1 traffic, and this access list. Now I go to the interface of this, which is FA0/0, and I just call this particular statement. I say access group so and so number 10 in the in facing direction. Now what happens is my traffic for telnet is going to get classified. Okay, all my traffic is getting classified now. Okay, that is happening because of my ACLs on the interface. So my traffic is getting classified. If I get some traffic for telnet, the counter will increase. So let's say I got one traffic, then I got second traffic, I got third traffic, fourth traffic, might be 10th traffic. So basically the traffic is getting classified. This is called as classification. Okay, you put the access list, you try to understand what kind of traffic is it, because you need to know what kind of traffic, right? So in the case of router, it was simple. You can put access list. Okay, and this basically access list, what happens is uh, so basically what happens is when the IP packets are being sent. Okay, if you just try to check them on Wireshark, you're gonna see that the header of IP packet has something for TOS. You might have heard about this component. So where do we see this TOS? If I take you to IP packet header, so they contain some special components. So you see here type of service. Okay, now this is used for QoS classification. Okay, basically they are a 8-bit, something like 0001111, some in this format. Okay, I'm gonna say that this is a important traffic, so set so and so. Let's say if this is not a important traffic, then I'm gonna say set 000. So basically type of service is where you classify your traffic. Okay, So that is the main field which is gonna help QoS traffic. So you're going to do classification, and you are going to mark that particular traffic, what kind of traffic it is. Okay. So in the case of IP address, we just saw that it was inside the header. But what about in the switch? So in the switch, in the VLAN packet, especially the trunk, there's something called as VLAN tagger or VLAN ID tagging, right? Uh, so in the case of VLAN tagging, if you just expand that particular component, one among that component, there is something called as priority. Now that is important for QoS classification and marking. Okay, if I show you Ethernet header, so I'm looking for a trunk header. Okay, this one, but this is not complete. I want something for VLAN identifier. Yeah, this one. Okay, so in this case, this is the case in switch QoS marker and classification. So this is how the priority is being set. Okay, this is VLAN ID, or we can say that in the case of trunking, the tag which gets added up. Okay, VLAN tag. So basically it consists of these many components. So this is that important component for QoS. Okay, in the case of router, we had that TOS, terms of service. Okay, so these are the two components which is uh, classifying and marking the traffic, and it's gonna tell us what kind of traffic is it, and what is the priority. Okay, regarding so this was the first one where I said classification and marking, where we are gonna see what kind of traffic is it, and then we are gonna mark the traffic. Now let's talk for congestion management. So in the case of congestion management, let's say if I have router 1 which is receiving some traffic. Okay, receive, I can also say that it's ingress in nature, and then I have router 2. So basically this is nothing but egress in nature. Okay, and then over here I have my output Q. Okay, and also this act as transmit. So in the case of congestion management, now we will talk from the output queue point of view. Let's say if the traffic hits here, okay, and R1 has to process the traffic. So basically all the traffic, it could be telnet, it could be SSH, it could be voice. They are taking a single, uh, I can say a single queue. Okay, a single buffer, or I can say that a single outgoing buffer, outgoing buffer. Okay, now what happens is all the traffic is just taking one queue. Now that can lead to issue. So we need to prioritize, or we can set a way that we have multiple queue. In the sense, let's say I have R1 here, my ingress traffic. Okay, before sending it to R2, I have multiple outgoing buffers. So like something like this: Q1, Q2, Q3, Q4, and then it's taking to R2. Okay, so this is congestion management. Instead of sending all the traffic in one single queue, or one single outgoing buffer, so what happens is, your, let's say one of the voice packet is stuck. Now it is congested. How do you say that you are very important to us, let's give you more better way to go to the second box, right? So now this queue can be set with percentage. I give 25% weightage here, I give 10% weightage here, let's say I give 75% weightage here, right? So this is a part of congestion management. If you get something, how do you send it in a better way to the next box? Okay, the third one here, after classification and marking, after congestion management, the third one is policing and shaping. This is very important. So in the case of policing and shaping, it's about discarding. Okay, discarding is like a total dropping. Or in the case of shaping, it's about uh, holding. Okay, or queuing. Okay, remember this: policy is going to drop your packet, whereas shaping is going to queue your traffic. For example, let's say if I had two routers, R1 and R2. Okay, there are two routers, and I'm just sending my packets. Now let's assume this is ISP and this is customer. Okay, and we need policing in the case of ISP end, because let's say customer purchased something, a bandwidth for 200 megabits, but since you don't have any restriction, he's gonna make use of the complete 1000 megabit. Now how do you set a restriction? You're gonna set a restriction saying something goes above. So let me draw a chart. Okay, let me say this is 200 mbit. Okay, and this is 1000 mbit. Now your customer who paid for 200 bit, his traffic is going at 100 mbit or 900 mbit. Okay, so his traffic is over here, but he should have been limited to this level. His level was this, but his traffic is over there, right? So that is not his mistake. The mistake is yours, that you don't have any sorts of way to limit the traffic. Now what you do is, you can set policing. So as soon as you do a policing, the traffic over this is now dropped. Okay, the traffic gets dropped. So basically his traffic will always be follow this pattern. Okay, now the problem with this kind of issue is, let's say for some reason his traffic was idle for some time, might be non-business hours, or after 5 p.m. or 6 p.m. the traffic was just at the lowest level, and in the morning, first morning, his traffic just spiked, right? So what happens is, his traffic will get dropped, right? But that's also leading to a bad experience from customer point of view, because his traffic, just for let's say 10 seconds, he had a spike for his you also know the same thing happens in respective to our CPUs and RAM also. When we boot up some router or a switch, initially it takes some time, but then it gets stabilized, right? So that doesn't mean that when it is hitting that peak we put some restriction and block the performance, right? Similar way, it's not good we set some restriction at this point. We can put a restriction in such a way, if the spike is for like 10 millisecond, within a 10 millisecond, then yes, he can go and hit the maximum. We are going to allow it. Okay, and his traffic must come down after 10 millisecond or before 10 millisecond, otherwise he's gonna get the QoS policing, which is nothing but he's gonna get dropped or discard the traffic. Okay, so this is a good way where you can limit your traffic, customer traffic. If there is a peak or a sudden peak, then those traffic will get dropped immediately. But also at the same time, we are giving them certain time frame where basically uh, they don't end up with a bad impression. Okay, so that particular time frame or that particular uh, rate which we have allowed the customer, we call it as CIR. Okay, it's called as committed information rate. So this is a committed information rate which the ISP will commit to the customer, that your sudden spike for 10 millisecond is good for us, but anything above that or anything which takes more time, we will just drop it with the help of QoS policy. Okay, so customer will be happy and he's good with that. But there's one more issue now. Let's say customer said, I don't want to drop it, I don't, because let's say he's not happy with the drop. Okay, the drop of 1 minute or 10 minute, we don't want to drop. Instead, give us a better solution. So there's one more solution where we are gonna put those packet, those which are exceeding the threshold, we will put them under queuing. Okay, now what happens is, let's say this was the 200 megabits and this is 1000 megabits. Okay, now this is the line. Okay, his traffic for any reason will not go up. Instead, his traffic will be put up on queuing. Okay, and the traffic will follow this line. So basically traffic is getting hold or it's going to queue. Okay, there is nothing called as exceeding the line here. There's no data which will exceed this particular line set, because we have put something for hold. Okay, if the traffic just comes up, what happens is it's gonna add delay to those packet. Okay, a packet which used to take 1 millisecond, let's say one packet takes 1 millisecond, now all of a sudden 100 packet came up. Now you just added lot of delay to them. So basically now once you add the delay, the traffic will start going in this direction. Okay, this would take much time. Let's say in the case of policing, you send 100 packet and you took like 10 millisecond to send 100 traffic, but might be due to the peak and all the limitation, there was some traffic dropped. Okay, here you're sending 100 packet, chances are you get 100 packet once again because there is no drop. And if the queuing is not very bad, if the interface is still processing the packet, then the traffic is actually traveling in a slower pace, right? So there is chances you get 100%, or I can say at least 99%, because we are not gonna drop any traffic. We are just trying to add the delay to this. Okay, so that is fine. We will not do this for a voice traffic, because this kind of delay will just spoil the conversation between the two users. Okay, but we can put this kind of practice while downloading something or while watching a YouTube. I don't want my packets to be dropped, but at the same time I'm okay for wait, because you might have observed sometimes the YouTube goes to buffer, right? They will take some time, but they will come back. They will not just drop something and start from some middle portion or something. It's just gonna put the or add the delay to those videos, right? Fine. So there's the last one under QoS tool, which is called as congestion avoidance. Okay, so to understand this topic, you must know what is TCP windowing, what is flow control. Okay, what do you understand by sliding? These are all topics from TCP. Okay, these are the TCP advanced topic. Say for example, if I have host 1 and I have host 2, okay, and I'm making use of a TCP transport channel, which is a reliable in nature. What do you understand by reliable? If there is a packet sent, packet number 1, there should be the acknowledgement sent by the other host saying that I have received the packet. Now the packet 2 will be sent, and then it's gonna send the acknowledgement. Okay, similar way there will be another packet, packet number 3, and there would be a acknowledgement number 3. Now you see, for every packet there is a acknowledgement. Now problem with this type of flow is your interface or your buffer is filled with unwanted acknowledged packet. Okay, so what we are gonna do is we are gonna increase the windowing. What is windowing? Which step the window get negotiated? It's in your three-way handshake. If you remember the three-way TCP handshake, okay, first the SYN packet will be sent. It's gonna send the SYN ACK, okay, and finally the acknowledged packet will be sent. Okay, now in this three-way step there will be the windowing or the window size getting negotiated. That is nothing but the receiver is gonna send some window size. It's gonna say that don't have to send one packet at a time. I'm free enough to accumulate 5 packet at a time. That means now host 1 is gonna send 5 consecutive packets, okay, towards H2, and then H2 is gonna send a acknowledgement packet. So 5 packets, 1 acknowledgement. Once again there is 5 packets, there is 1 acknowledgement. Okay, this is called as fixed window. Now the problem is, what if H2 had more buffer left? It could handle 10 packets now. Okay, but since we had a fixed window, it was sending 5 at a time and 1 acknowledgement, and then 5 at a time and then acknowledgement, right? So we have something called as sliding. Okay, now in the case of sliding, H2 is gonna tell what is its potential to take it, so it can change every time. So basically first it took 5, might be second time also it took 5. Now it is free enough to take 10 packets. Okay, so once the 10 packets are being sent, then H2 is gonna reply back acknowledge. and that acknowledge is to put a hold on H1. It's gonna say I am all full for now, just wait for some time. Okay, so once the acknowledge packet is sent, then the H1 is gonna resend the remaining packet. Now this is called as TCP windowing, flow control, and sliding. Okay, now where is this congestion avoidance coming up in QoS? So let's say, let's say if I had the router 1 and router 2. Okay, the same example that I had, I sent the three packets, one acknowledgement, and then finally, and then we went with the uh, a sliding kind of window where I could send more number of packets, then acknowledgement, then more number of packets, right? So let's talk from the output queue now. So what happens is, how does this increases its slider depending upon the output queue. Okay, Eh, the R2 is gonna say that I can accumulate 5 packets. Okay, so H1 will send consecutive 5 packets, and then R2 will send a acknowledgement. So how does that R2 decide what is the availability of this output, right? So let's say if this is the output queue, it had some packets already, one, two, three. Now there was space for another 3 packets. Okay, now what happens is it's gonna send the 3 packets that's get over here. So once this packet has been set in the buffer, now if you receive one more packet, that particular packet will be dropped because there is no space in the output queue, right? There's no space in the output queue. Now here is where you have your congestion management tools like WRED. Okay, now these are some tools where we also have tail drop. Okay, the packet which is getting dropped, we usually call it as tail drop. Okay, and the tool which we are going to use is called as red, WRED. Okay, now what happens is, over here in the output queue we have a table. Let's say we have a table here. Okay, and I have my output queue. So I gonna say that this is fully empty. That means if a traffic is coming for SSH, I know that there's lot of room for it. Let's say this is all filled traffic for a telnet. So I'm gonna say that don't entertain any more telnet traffic because my buffer is completed. Okay, so I have to wait. So basically you're setting your output queue to avoid the congestion. If you don't do this, your traffic, among the thousands of packet, might be there are 50 good traffic which has to be taken care immediately. But since you don't have this kind of segmented or kind of a distributed output queue, these 50 packets will be just on a hold, and chances are that they will be dropped if they are not taken care before the hold timers. Okay, so we are gonna set this table. We are gonna push them accordingly to which block they belong to, and we just make use of the congestion avoidance tool so that we can go with a smoother transaction. Okay, or a smoother traffic flow. Well, so that ends your QoS traffic. QoS. There's nothing much here. It was just a describe here. QoS component, QoS policy, and the concepts of QoS. Okay. And yeah, regarding the lab, I will include in the class note, so you can do it on your own. So basically, as I told you, we just need access list. Okay, these access lists are used for classifying. Say for example, over here, I'm gonna write a access rule. Okay, and I'm gonna define what kind of traffic I'm expecting out of this. So I said 23 TCP. Now this traffic is nothing but the telnet traffic. I'm gonna define my QoS. Okay, I'm gonna call this over here, and then I'm gonna apply this. Say for example, I have R1, I have R2, I have set my QoS here. Okay, on this interface, gig 0/1. And the moment you do the test, let's say this is 192.168.12.2, you will see the traffic hitting this interface. And whenever I make use of the show command, I can see the telnet traffic. Okay, so you see that 11 packets being received. So you have your class map being set. So this is how we make use of the classification, and we are marking the traffic. All right, guys. So let me know if you guys have any doubt. I'll pass on this workbook, and I'll pass on the notes for you guys. All right. So good night, and let's meet up in the next class. Have a nice day, everyone. See you soon. Yeah, some documents are not available for download, but I have given the G Drive link long time back in the group, so you can download all the notes from there itself. Okay, take care, and we'll meet up in the next class. Okay, see you.